next speaker is Gaëlle Tanguy. Gaëlle, she works in InnovaDryer also, and she's a partner with our team too. She worked with Professor Italo some years ago in this postdoc of Italo, and last year she was the advisor from one of our students from Viçosa, Erica. And thank you, Gaëlle, to be with us and share your knowledge with us today.
Okay, thank you, Antonio. Thank you first for your invitation to this event. I'm very glad to participate to this event. So it's my presentation. Oops. Okay, so first, my presentation deals about the falling film evaporators, and it's divided in two parts. The first will present some general elements relative to falling in falling film evaporators, and then the second part is dedicated. Second part is dedicated to more experimental data that we obtain in our lab during experiments. But to start, I will do a quick presentation of InnovaDryer and the STLO research unit. So InnovaDryer was created at the beginning of this year. It results from the merger of INRA and IRSTEA, and it's that are two French public research institutes. And it's now the world's leading research organization specializing in agriculture, food, and the environment. Faced to the major global concerns such as climate change, biodiversity loss, resource scarcity, growing world population, InnovaDryer's main goal is to develop solutions that involve multi-performance agriculture, high-quality food, and sustainable management of resources and ecosystems. And the Institute carried out targeted research on these topics. Just some figures about the Institute. It is a community of about 12,000 people that are in 268 research units, experimental research units, and support units. They are located in 18 research centers, and the Institute is divided in 14 scientific divisions. So now concerning the research unit where I worked, so it is STLO for Science and Technology of Milk and Eggs. It is located in Brittany, in the western of France. And the two study objects, milk and eggs, are explored in the disciplinary areas of biochemistry, processing, and microbiology. So we will explore the structuration and destructuration mechanism of matrices, from structural characterization to digestion. We will study some dairy processes, such as membrane filtration, concentration, vacuum concentration, spread drying, and cheese making. And we will try to go towards sustainable dairy systems. And concerning microbiology, we will explore the microbial interactions between in-food matrices and host cells. The specificity of the lab is that we conduct research according to a multidisciplinary and multi-scale approach, and we benefit from two high-caliber facilities. So the dairy platform, which is an experimental facility at pilot scale that is about 800 square meters, and we've got a biological resource center that is dedicated to food bacteria. So if you want to have more information, you can have a look on the website. You have the link at the bottom of the slide. So let's start to talk about concentration and falling film evaporators. So the concentration by vacuum evaporation is a widely used operation in the dairy industry because it is used as an intermediate step for the production of powder in combination with air drying. And it is used too for the production of concentrated products such as sweetened condensed milk or concentrated yogurts. And the maximum dry matter content is determined by the maximum achievable viscosity of the concentrate at the outlet of the evaporator. So depending on the product, The viscosity, and generally, as viscosity depends on several factors such as temperature, shear rate, and dry matter, the limiting operation for falling film evaporator would be expressed in terms of maximum dry matter content. So it will be for skim milk about 50% dry matter, for whey about 60% dry matter, and for sweetened condensed milk, it would be about 70% dry matter. So the operation is carried out in falling film evaporator. So on the slide, you have the presentation of the 4 effect falling film evaporators. So you can see the calandria, the 4 calandria, the separator. And at the end of the equipment, we've got the condenser, where the vapor from the product are condensed that allows to create vacuum in the equipment. So the product is first plated and it's distributed at the top of the falling film evaporator. So you've got a distribution device, and the manufacturers paid much attention to this part of the falling film of this equipment, because it may contribute to the falling. I will explain this part later. But the objective of the distribution device is to distribute uniformly the product into the tubes and to have an early establishment of a true film conditions in order to cover the complete surface of the tubes. And then, you have the products that flow inside the tube, and it's only a thin film, it's only 1 to 2 millimeters. On the shell side, you have the steam. The steam will condense and provide the heat for the evaporation of water. So the efficiency of the evaporator will be defined according to the heat transfer between the steam and the product, and the performance of the evaporator is expressed in terms of evaporation rate. Concerning the condition in evaporator, it's about 70 to 48 degrees Celsius. So the dry matter will increase and it will depend on the product. And the residence time is between 10 to 20 minutes. And so in the evaporator, we have 3 parameters that evolve all along the evaporator's time, the temperature and the concentration. So the falling is defined as the deposition of particles on the inner surface of the evaporation tubes. So this supplementary layer at a low thermal conductivity, and it will decrease the global heat transfer coefficient, and it will decrease the evaporation rate. The only action that has the operator to improve the evaporation rate is to increase the temperature difference between the steam and the product, but this action have also a negative effect on the falling because it will enhance falling. So the only solution will be to clean the equipment, but if you do more frequent cleaning of the equipment, you will increase the cost, the operating cost, because you will have to stop the equipment to clean it. You will have to use chemicals, you will have to use water, so it will increase the operating cost. And the second effect of the falling is that you can, the particles that are on the surface of the evaporation tube, they can be potential growth sites for thermophilic bacteria. And the formation of biofilms is a real industrial problem because the biofilm made to develop in the operating range of the falling film evaporator. And moreover, you can have a release of particles into the product that will decrease the quality of the product. So falling will compromise the process efficiency with higher energy cost and higher cleaning cost, and it will compromise too the product quality. So in the falling film evaporator, there are some specific features that will promote the falling. The first one would be the falling can be due to a breakdown of the falling film that is due to the incomplete weighting of the tubes. For example, if you have not a complete weighting of the tubes, you can have the film that flow in rivulets on the inner surface of the evaporation tubes. You can have the formation of dry patch. you can have some products that are adhered on the surface of the inner surface. And so this product on the surface can burn and will have falling. And this incomplete weighting of the tubes can be due to a lower mass flow rate per tube. So you have to check if you have a good mass flow rate at the inner of the evaporation tube to be sure to have a complete weighting. But this incomplete weighting of the tubes can be due to an unequal and unsteady liquid distributions at the top of the evaporation tubes. That's why it's important. That's why the design of the distribution device is very important. The second feature that may promote fouling is the low shear stresses exerted on the fouling film. As the fluid is flowing by gravity, you can have the deposition of the foulant particle on the inner surface. Moreover, you will have a viscosity that increases, the viscosity of the product will increase, so the deposition is favorable. The last point that will promote the fouling of fouling film evaporators would be the evolution of the product during concentration. Because during concentration, you have all the compounds of the product will be affected by the concentration. It is the case for the mineral fractions, proteins, and the lactose. If we look at the mineral fractions, you will have modification of the ion equilibria. So we'll have an increase of the ionic strength. If we look at the modification of the ion equilibria, you can have an insolubilization of some salts, such as calcium phosphate, with the release of hydrogen protons. And these hydrogen protons will participate to the decrease of pH. You may have too the transfer of soluble calcium to the colloidal phase. And the ionic strength, the increase in ionic strength would lead to a decrease of the pH. Concerning the proteins, you will have a closer packing of proteins that will favor protein associations, combined to the decrease of pH and the transfer of soluble calcium to colloidal phase will promote to the protein association. Then you may have two lactose crystallization if the solubility threshold is exceeded. And all this modification of into the product will have effect on the modification of the physical properties, such as an increase of the viscosity, a decrease of the surface tension, and an increase in the density. And again, all this modification of the product will have impact on the composition of the fouling deposits. So in first approximation, we could consider that a fouling film evaporator is comparable to an heat exchanger, a latent heat exchanger. But as we have seen previously, there is different operating conditions between both equipment. In terms of concentration, you have in terms of temperature, in terms of residence times. In the literature, there are really few studies about the fouling of fouling film evaporators. Nevertheless, the authors that studied fouling, they suggest that the mechanisms of fouling and the composition of deposit might be different in heat exchanger and fouling film evaporators. So it means that we need to adapt the cleaning procedure to evaporators. There is few studies, but there is a complete study that was done in 1994 by Jornik and Brickman, and they studied the fouling of fouling film evaporators and heat exchangers during the concentration of milk and whey. And this table presents you the composition of deposit. So it's in percent, is the composition of the deposit per ton of treated product. And it's they compare the composition of the deposit inside after the heat treatment of whey at 28% dry matter at 70 degrees Celsius and during 90 seconds. They compare the deposit, the composition of the deposit, to the decomposition of the deposit obtained after the concentration of whey from 28 to 55% dry matter. And they noted that there was less proteins in the deposit in the fouling film evaporator, there was less phosphate ions, but there was more citrate ions. Based on this study, we develop a research topic in the lab, so in the science and technology of milk and eggs. We developed a project about the falling film evaporators, and the main objective was to understand which components contribute to the falling film evaporators during the concentration of their products. The objectives are to propose solutions to limit fouling and to adapt the cleaning procedures to the nature of the deposit form. To conduct the experiment, we developed a specific methodology to study fouling and to recover the deposit form. So in the next part of my presentation, I will give you the detail of this method and some results that we obtained for the concentration of different ways. But the method is based on the use of a falling film evaporator at pilot scale, and we determine the nature of the deposit according to two methods: a mass balance on the composition of the concentrates at the inlet and at the outlet of the evaporator, and a direct determination of the compounds in the deposit using a specific device that we have developed in the lab. And we apply to the concentration of different ways. So this is the equipment that we use. You have a picture on the left, and it's an equipment that is installed on the dairy platform. It's a single effect falling film evaporator that is composed of 3 calandria in series. Each calandria is composed of only one tube, and the very specificity of this equipment is that the 3 calandria are connected to the same condenser. So compared to industrial falling film evaporator, we don't have a gradient of temperature, but we have a constant temperature that is the evaporation temperature, and that was fixed to 60 degrees Celsius. So as you can see on the scheme, so the liquid goes through is braided from 20 to 60 degrees Celsius, and it goes through all the evaporator. And at the end, when the concentrate became the inlet product in order to produce concentrate at different concentration factors. So we did several successive runs to produce the concentrate at different concentration factor, and we characterize the composition of the concentrate. So to go further in the study, we developed a specific device. So it's a system that is installed at the top of the 3rd calandria, so you can see on the picture. So it's put on the existing calandria at just at the top of the 3rd calandria, and it's composed of 3 sections that are amovible, and we can disconnect all the equipment to recover the evaporation tube where the deposit is formed. So the experimental procedure then is to concentrate the product into the evaporator, to rinse with softened water in order to avoid the addition of minerals into the deposit. We dismantle the device and we recover and analyze the deposit. So in terms of characterization that was done on the product, for the concentrate, we characterize the concentrate in terms of dry matter, ash content, total nitrogen content, total cations, total anions, soluble phase, and soluble cations and soluble anions. And we did a mass balance between the inlet feed product and the outlet concentrate. And then on the same graph, and for each compound, we plot the concentration of each compound in function of the concentration factor. So we put the experimental total ion content, the experimental soluble ion content, and the calculated total ion content. The calculated total ion content is the product of the concentration factor by the ion content is an initial liquid product. From this graph, then, we can determine the quantity of compound that is deposited in the evaporator and the quantity of compound that become insolubles in the concentrates. Concerning the deposit, so we characterize deposit in terms of dry matter, total nitrogen content, total cations, total anions, and we did Fourier transform infrared spectroscopy analysis, where the objective is to determine the functional groups that are present in the deposit. But the main disadvantage of this system is that to carry out the analysis, we need to have enough mass of deposit, which is not the case. So sometimes it's a main drawback of this system. But with these two, we have two complementary methods to know the composition of the deposit, an indirect determination of the composition of the deposit using the composition of the concentrate, and a direct determination of the composition of the deposit. And we start the study with hydrochloric acid whey. So it's a byproduct from casein industry. And we used this product because it's known to be a foulant product. So this product is characterized by a low pH. It's about 4.6. It has a low dry matter content, about 5.9%. And in terms of the mineral, concerning the mineral fractions, it contains calcium, potassium, inorganic phosphate, and citrate, as well as chlorate in a high quantity due to the addition of hydrochloric acid for the preparation that is due to the production of the hydrochloric acid whey. So as expected, we obtained a fouling of the evaporator. So there was a white deposit on the inner surface of the evaporation tubes. We noticed too the presence of insolubles in the more concentrated produce. And we noticed too a sharp decrease of the pH of the concentrate in function of the concentration factor. We followed the evolution of the total nitrogen content of the ash content in function of the concentration factor. And as you can see on the both graphs, that there is a linear evolution of the total nitrogen and ash contents in function of the concentration factor. So we can conclude that there is no significant losses of total nitrogen and ash content in the evaporator. We did the same thing from some ions, that the main ions present in the hydrochloric acid whey. So concerning calcium, as you can see on the graph that presents the evolution of the calcium content in function of the concentration factor, there is a part of the calcium ions that are in the deposit. So they are in the evaporator, and a part of the calcium ions become insoluble in the concentrate. And we compare with the two anions that may be associated to the calcium. And what we've seen is that concerning the inorganic phosphate, there is only a small part of the inorganic phosphate ions that become insoluble in the concentrate, but no inorganic phosphate remain in the evaporator. On the contrary, for the citrates, we notice that a large part of the citrate ions were in the deposit, and a large part of the citrate ions remain insoluble. So by this method, so only by the characterization of the concentrate, only by the comparison of the concentrate, of the composition of the concentrate, we seen that there was a preferential reaction between calcium ion and citrate ion, and that the deposit formed in the falling film evaporator was calcium citrates. And this result was confirmed by the analysis of the deposit formed during concentration. So this table presents the composition of the deposit in terms of total nitrogen, in terms of calcium, in terms of ion present in the deposit. And as you can see, a large part of the deposit is formed of calcium citrate. And what is interesting is that using this direct determination, we get a molar ratio of 1.3, molar ratio calcium over citrate, equal to 1.3, which is very close to the molar ratio of the tricitrate dicalcium, which means that the structure of the calcium citrate present in the deposit should be in the form of tricalcium dicitrate. But the direct analysis of the method showed that there was some proteins too and some phosphate. And finally, the spectroscopy analysis, so with Fourier transform infrared spectroscopy, it confirms the presence of protein and phosphate, but the absence of lactose, which is quite surprising because lactose is the main compound of the whey. We did we go on the study with a concentration of lactic acid whey. So both whey have the same pH, roughly the same pH, the same dry matter content, and in terms of composition, it's roughly the same. But they differ in terms of the composition of the mineral fraction. So there is more chloride ions in hydrochloric acid whey, but it's normal because we have had hydrochloric acid in the whey. But the main difference is concerning citrate ion and lactate ion, because there was no citrate ion in lactic acid whey, but there was a large quantity of lactate ions. And what we've seen that there was no deposit in the evaporator when we concentrate lactic acid whey, no insolubles in the concentrates, and a low decrease of pH. And if we look at the evolution of the calcium inorganic phosphate and lactate content during the concentration, so in function of the concentration factor, we've seen that there was no losses of calcium and inorganic phosphate or the lactate in the evaporator. So then we try to interpret the results, and we studied the ion association in acid wheys during the concentration. And we took, for example, the concentrate at concentration factor 7.6 and pH 3.4. And at this pH, the species that are present are H2PO4 minus and H citrate 2 minus and H2 citrate minus. Both will react with calcium to form calcium phosphate, either dicitrate tricalcium. And we used the association constant defined by Holt to have an estimation about what was the preferential reaction. So you have to know that this association constant was defined in conditions totally different that the one the one present in the evaporator. It means that it was determined in milk ultrafiltrate at unique strength equal to 0 and at equilibrium, but it could be useful to have an estimation. And we can see that the reaction of calcium and H citrate 2 minus is preferential. We did the same thing with the concentrate of lactic acid whey at a concentration factor 8.3, and at the pH 4.2 H2PO, the species present at H2PO4 minus and lactate both react with calcium, and there is the formation of calcium phosphate or lactate calcium. But the association constants are quite similar. But in this product, there is the quantity of lactate is higher than the quantity of phosphate. There is a high solubility of calcium lactate and an increasing solubility of calcium lactate with temperature. So this result explains that there is no deposition of lactate calcium or calcium phosphate in the evaporator. So to conclude from this study, we determined that the calcium citrate contributes to the fouling of the falling film evaporator during the concentration of hydrochloric acid whey. that there is no falling during the concentration of lactic acid whey due to the absence of citrate ions and the high quantity of lactate ions. We go on this study with two other wheys. It was milk ultrafiltrate and microfiltrate. So both wheys are a pH of equal to 6.7, and they have the difference between both is the presence of proteins in milk microfiltrate. And we've seen that for ultrafiltrate, there was a fouling due to calcium phosphate, but in microfiltrate, the proteins interact with calcium phosphate and limit its insolubilization. So to conclude, in order to have an idea of which compound contribute to the fouling in falling film evaporator, you have to take into account the pH, the mineral content, as well as the presence of protein, because there are some biochemical parameters that determine the formation or not of the fouling deposit in falling film evaporators. The next step of our study, so we go on to work on this topic, and we try to identify the conditions that favor fouling and the ways that could limit it. So we modify the nature of the product in terms of pH, ion content, in terms of proteins, but actually we are doing a screening of ways with different composition Abla scale to look at what are the elements that contribute to the fouling of falling film evaporators. We try to modify the process parameters, evaporation temperature, temperature difference between the product and the vapor. And the question is, what about the pretreatment of the product to limit fouling? And we go on to characterize the deposit form in terms of nature, structure, in order to adapt the cleaning procedure. Thank you for your attention. So if you have some question.
Thank you, Gaëlle, for excellent presentation. Your field is really important for the dairy industry. Unfortunately, we have no time for question, but I would like to thank you for your partnership with Inovaleite, with the work with Erica, and I hope you can continue in, I know that you are continuing with Professor Italo that we talk with right now. Thank you.
Thank you again for your invitation. Thank you.